Hello, this presentation is entitled Synergies between in-loop and out-loop mapping for HDR-PQ content. I am Edouard François from Interdigital. Adaptive video content mapping is a video processing tool that has been studied for various purposes. It can be used as a display adaptation tool for adapting the video content to the display capabilities. It has also been explored as a coding tool for improving video compression for diverse types of content, such as SDR, wide color gamut, WCG, or HDR. For a video compression purpose, the approach consists in adapting the video signal samples based on their statistical properties in order to better exploit the video signal range. This is, for instance, illustrated in the figure below, where the left side corresponds to the input signal with its LUMO signal histogram, and the right side corresponds to the mapped version of this original signal, where it can be observed that from the histogram that the LUMA signal code words have been expanded and the actual signal range is wider than the original one, which leads to improved compression because the quantization is more performing. Video content mapping has been actually explored in multiple studies, and what we mention here is limited to the former work achieved in the context of standardization. So first, out-of-loop approaches have been investigated in MPEG during around 2015 and further submitted to the call for proposal that has preceded the development of the VVC standard. Alternatively, in-loop content mapping has also been studied and submitted to the same call for proposal. Later on, these two approaches have been further evaluated in core experiments of the JVET group, who was in charge of defining the VVC standard. So on one side, we had the dynamic range adaptation, which was studied as the out-of-loop mapping solution, and LUMA mapping with chroma scaling, LMCS, which was studied as the in-loop solution. Eventually, the in-loop approach was adopted in the VVC design because it was considered as offering several benefits, and three of them are mentioned here. In-loop mapping turns out to be more flexible regarding temporal variations of the mapping function. It offers coding benefits for a wide variety of content, SDR, HLG, PQ, and it does not require an additional buffer to the decoded picture buffer DPP of the decoder, which is not the case for the out-of-loop mapping approach. So the main purpose of this study, which is reported in this presentation, is to compare these two designs, in-loop and out-of-loop mapping, for the specific case of HDR-PQ content. What is also reported is the evaluation of the possible synergies between these two approaches. So let's first have a look to the LMCS design as it was adopted in the VVC standard. LMCS is an in-loop solution as described in the picture below for the decoder side. So one important characteristic of LMCS is that the reference pictures which are stored in the decoding picture buffer are actually in their original non-mapped domain. So how does it work? First, regarding LUMA, there is a forward mapping which is applied to the temporal prediction of the LUMA component. intra-prediction of Luma is actually achieved already in the map domain. Once the Luma signal has been reconstructed in the map domain, there is an inverse mapping function which is applied prior to the in-loop filtering to go back to the original non-map domain. For chroma, the mapping consists in a cross-component inverse scaling of the chroma residual, and the scaling factor depends on the average local Luma samples. The scaling factors correspond actually to the slopes of the Luma forward mapping function or inverse mapping function. In terms of signaling, only the forward mapping function parameters are signaled in the structure called adaptation parameter set, APS. So the Luma mapping function is piecewise linear, and what is signaled are the slopes and the offsets of each segment. The inverse mapping function, as well as the cross-component chroma scaling factors, are actually inferred from the forward mapping function parameters, so they don't need to be signaled. In the actual reference encoder implementation, called VTM software, the mapping function derived at the encoder can be of two types, depending on the input signal. For HDR-PQ signal, the Luma mapping function is fixed, which means non-content dependent and applied for all pictures. And the picture on the right of this slide illustrates the forward and inverse Luma mapping functions applied for HDR-PQ content in the VTM. For SDR and HLG content, the mapping function is adaptively derived and adaptively enabled or disabled at picture level. Let's now have a look to the out-of-loop approach. The process consists in a pre-encoding forward mapping and in a post-decoding inverse mapping to go back to the original non-mapped domain. In the implemented design for Luma, the mapping is intra-component. For chroma, the process is either intra or cross-component. This is further explained in the next slide. The signaling of mapping parameters is performed typically using an SEI message that signals the Luma mapping function as a piecewise linear model. The chroma mapping function are signaled as piecewise linear model or inferred from the Luma mapping function. This slide illustrates more specifically the Luma and chroma mapping processes. So we have here the equations of the intra mapping process applied to Luma and of the two options for chroma, which are either intra mapping process or cross-component mapping process. And more specifically, in the case of the cross-component mapping process, you can observe that the slope that is applied to the chroma component depends on the Luma component, which is called Y colloc. The picture below depicts the inverse Luma mapping function typically used for HDR-PQ content. And what is observed is that this is the same function as used in VTM LMCS for HDR-PQ. And the right graph depicts an example of cross-component chroma scaling function corresponding actually to the slopes of the inverse Luma mapping function. Complexity of the out-of-loop mapping is quite limited, as it overall leads to 1 or 2 multiplications per sample and 2 or 3 additions per sample, and a few shift operations. So if we, for instance, compare this process to the adaptive loop filter of EVC, ALF, this is quite negligible. So let's move to the test part, experimentation part. So in this slide, we depict the test conditions used for the evaluation of these two approaches. First, VTM12 has been used, and as test content, we have used the HDR-PQ content defined in the JVET common test conditions. 3 configurations are reported: all intra, random access, and low delay B. In terms of metrics, we report the results for the HDR-PQ objective metrics, which are delta E 100, PSNR L 100, WPSNR Y, U, and V. In the current slide, we indicate the main differences between in-loop and out-of-loop approaches. The Luma mapping is exactly the same for both approaches. Chroma mapping is achieved differently in both cases. In the in-loop LMCS, chroma scaling consists in scaling the chroma residual. The scaling factor is dependent on the average value of Luma samples neighboring the current video processing decoding unit, which is actually a 64 by 64 Luma block. In the out-of-loop mapping, chroma samples are mapped using a Luma-dependent scaling factor. There is one scaling factor per sample derived from the collocated reconstructed Luma sample. And the chroma scaling function is defined as a continuous piecewise linear function, while in LMCS it is constant per segment. This is illustrated in the graph where the blue curve corresponds to the scaling function used in the in-loop LMCS, and the red curve corresponds to the scaling function used in the out-of-loop chroma mapping. In the first reported test, we compare in-loop LMCS to out-of-loop mapping. So in this test, the reference corresponds to LMCS enabled and out-of-loop mapping disabled, and the test corresponds to LMCS disabled and out-of-loop mapping enabled. In red box, we emphasize the Luma-related metrics. What we can observe from this slide is that the coding gains are observed for all metrics, and we also see that the highest gains are observed in inter-configurations and in particular in low delay configurations, where a gain of 2.5% can be observed for PSNR L or 1.56 for WPSNR Y. Then we have performed a second test where we wanted to test the synergy between in-loop LMCS and out-of-loop mapping. So here again, the reference corresponds to LMCS enabled and out-of-loop mapping disabled. And the test here enables both tools. LMCS is enabled, out-of-loop mapping is enabled. And in this configuration, the in-loop LMCS uses the adaptive tuning algorithm defined for SDR and HLG, which means that LMCS performs a refinement of the HDR-PQ fixed mapping function used in the out-of-loop mapping. Again, in red box, we emphasize the Luma-related metrics. What can be observed is that the Luma metrics, so PSNR L and WPSNR Y, are noticeably improved compared to test 1. There is a slight loss in chroma metrics. However, the Luma gains are unbalanced, considered as more significant than the corresponding slight loss in chroma. So in conclusion, we can observe that there can be synergies between these two tools, out-of-loop mapping and in-loop LMCS for HDR-PQ content. This leads to the conclusion of this study. We have observed that out-of-loop mapping can provide improved coding gain over in-loop LMCS for HDR-PQ content. The second point is that these tools can synergize and lead to additional gains when they are combined. For instance, when using out-of-loop mapping with a static mapping function and in-loop LMCS as an adaptive refinement of the mapping function, we have observed those additional gains. It should be noted that the tests performed on SDR and HDR HLG content do not show noticeable impacts on the overall performance. The main reasons are that the VTM tuning algorithm for SDR and HLG is content adaptive and leads to temporal variation of the mapping function. But the out-of-loop mapping process is quite sensitive to temporal variations, as this can make the temporal prediction less efficient. That's why the tool or the two tools do not properly synergize for SDR and HDR HLG. This concludes this presentation. Thanks for your attention.